session. In this session, we will concentrate on properties of Laplace transform. First, Laplace transform of derivatives and integrals. So one by one we will see Laplace transform of f dash of t, where f dash of t is a derivative of f of t. So Laplace transform of f dash of t, what will happen? What is the answer? So based on a first principle method or by formula, it is 0 to infinity f dash of t e to the power minus st dt. Now this is according to the formula. Now this e to the power minus st and f dash of t both are a function of time, a variable, both are a function of t. So if we integrate this integration is based on integration of products. U dv is equal to uv minus integration of v du. So based on the integration of products, u dv is equal to uv minus v du. Now in this particular case, f dash of t and e to the power minus st, I will consider e to the power minus st as u and f dash of t as dv. This f dash of t as dv, because this v is integration of dv, so integration of f dash derivative function is f. So that is why I am considering here this as a dv. Now if I apply this formula to this, what will happen? U e to the power minus st u into integration of v dv means f dash of t, that means f of t, minus, this is in the limit integration 0 to infinity, and this is yet to calculate, so 0 to infinity v means f of t, integration of the differentiation f of t into du, differentiation of e to the power minus st, that is e to the power minus st into minus s dt. Now in this case, if I apply t is equal to infinity, if I apply the limits e to the power minus infinity f of infinity minus e to the power 0 f of 0, by applying the limits to the first one, minus into minus plus s into integration 0 to infinity f of t e to the power minus st dt. Now e to the power minus infinity means it is a 0, so 0, e to the power 0 is 1, so it is 0 minus f of 0 plus s into, what is this? 0 to infinity f of t e to the power minus st dt is f of s. So Laplace transform of derivative f dash of t equal to s f of s minus f of 0. So this is the Laplace transform of a derivative function. Next, Laplace transform of integrals, integration of f of t dt. So now Laplace transform of integration of f of t dt. So based on the formula 0 to infinity f of t dt e to the power minus st dt. Now here also the same thing. Integration of f of t as well as e to the power minus st, both are the function of t. So I need to use integration by products. So based on that, to apply this, now I will consider this as a v, this as a u. Reason is du comes here, differentiation of u. So differentiation of the integration is f of t. So that is why I will consider this as integration. So now what happens to this? So u into integration of v. So u is integration of f of t dt into integration of e to the power minus st, means e to the power minus s divided by minus s. This is in the interval 0 to infinity. Minus integration of v du. V means e to the power minus st by sorry, this is the dv by minus s into differentiation of integration, means f of t dt. Now when t is equal to infinity, what will happen? This is 0. So 0 minus, when t is equal to 0, this is 1. What about this? Integration of f of 0 means it is f of 0 only by minus s. Minus into minus plus 1 by s, integration of, integration limit is 0 to infinity f of t e to the power minus st dt. So now this integration from 0 to infinity f of t e to the power minus st dt is f of s. So this is equal to f of s by s minus, minus into minus become plus f of 0 by s. So Laplace transform of integral function equal to f of s by s plus f of 0 by s. So Laplace transform of different derivatives, Laplace transform of integrals. Next, property of linearity. Property of linearity says that if Laplace transform of f of t equal to f of s, then Laplace transform of k f of t, a constant, equal to k f of s. So it's a very simple, because Laplace transform of k f of t means 0 to infinity k f of t e to the power minus st dt. As k is a constant, k can be taken outside. So k into 0 to infinity f of t e to the power minus st dt. That is equal to k into f of s. This is a very simple property. So Laplace transform of k f of t equal to k into f of s. This is linearity. Now next, superposition. Superposition is Laplace transform of f1 of t plus f2 of t plus Fn of t equal to F1 of s plus F2 of s Fn of s. Now I will consider proof. Laplace transform of F1 of t plus F2 of t Fn of t based on the formula or basic principle 0 to infinity F1 of t plus F2 of t plus Fn of t e to the power minus st dt. This can be written as integration 0 to infinity F1 of t e to the power minus st dt plus integration 0 to infinity F2 of t e to the power minus st dt and so on. That means this is F1 of s plus F2 of s and so on. So this is the property of linearity and property of superposition. Next we will see the property of shifting. So in this property of shifting there are two shifting properties. So first we will go with first shifting property. Now according to this first shifting property, if Laplace transform of f of t equal to f of s, then Laplace transform of e to the power minus at f of t equal to f of s plus a. So first shifting property says if Laplace transform of f of t is equal to f of s, then Laplace transform of e to the power minus at f of t equal to f of s plus a. So let us see the proof. Laplace transform of e to the power minus at f of t equal to, based on the formula, 0 to infinity e power minus at f of t e power minus st dt. Now e power minus at e power minus st. So e to the power a into e to the power b is equal to e to the power a plus b. So based on that, this equation becomes 0 to infinity f of t e to the power minus s plus a into t dt. Now we know that this f of s equal to 0 to infinity f of t e to the power minus st dt. See, e to the power minus st minus t coefficient is f of s. So in this case 0 to infinity f of t e to the power minus s plus a into t. So this Laplace transform of e to the power minus at f of t equal to f of s plus a. So comparing with this and this, so this is the first shifting theorem. So second shifting theorem. Now, according to this, if Laplace transform of f of t equal to f of s, then Laplace transform of f of t minus a u of t minus a equal to e power minus as f of s. So Laplace transform of f of t minus a u of t minus a equal to e to the power minus as f of s. Now proof. Now Laplace transform of f of t minus a u of t minus a according to the formula 0 to infinity f of t minus a u of t minus a e to the power minus st dt. Instead of f of t minus a, u of t minus a is there, so as it is. Now, what is this u of t minus a? We know that u of t minus a equal to 1 for t greater than or equal to a, 0 t less than a. So, u of t minus a is 1 for t greater than or equal to a, 0 for t less than a. So, in this interval 0 to a, u of t minus a is 0. Up to a, u of t minus a is 0. A onwards, this value is 1. So, based on this, u of t minus a equal to 1 for t greater than or equal to a and 0 for t less than a, I will rewrite this equation as a to infinity f of t minus a e to the power minus st dt. F of t minus a e to the power minus st dt. Now let t minus a equal to m, change of variable. So when t minus a is equal to m, what happens to t? M plus a. What about dt? A is a constant, so dt is equal to dm. So what about the limit? When t equal to a, m equal to 0. So if I substitute t is equal to a, m becomes 0. When t is equal to infinity, m equal to infinity. So this integration, because of change of variable, 0 to infinity f of m e to the power minus s into m plus a dm. So e to the power minus sa, here integration is with respect to m, so sa acts as a constant, so it is e to the power minus sa integration 0 to m infinity f of m e to the power minus sm dm. So since it is a limit integration, irrespective of the variable m or t, it is same. So f of m e to the power minus sm dm is same as f of s. So it is e to the power minus as f of s. So Laplace transform of f of t minus a u of t minus a equal to e to the power minus as f of s. Next, Laplace transform of periodic function. Now, what do you mean by periodic function? A function is repetitive in the interval tau. That means, suppose a signal, if I consider this is one signal at tau, and if this signal repeats for every tau, this is 2 tau, this is 3 tau. So in every interval tau, it is repeating. So such signals are called as periodic signal or periodic function. So if this is f of t, now this signal can be written as tau plus tau 2 tau plus two tau, 3 tau, and so on. Now this signal as sum of this 0 to tau, this is only the waveform, these are zeros, so this plus tau to 2 tau, this is, so by adding all those things, it is equal to this periodic signal. So suppose if I take this as f1 of t, if suppose this I will take it as f1 of t, then what about this signal? Now this signal is shifted version of this. So this signal is a shifted version of this, and shifting is tau. So this I will write as f1 of t minus tau. This signal is shifted version of this, but shifting is 2 tau. So this I can write as f1 of t minus 2 tau. So mathematically I can write f of t as f1 of t plus f1 of t minus tau plus f1 of t minus 2 tau, and so on. Now what happens? The Laplace transform of f of t. So by the properties of superposition, this is Laplace transform of f1 of t plus Laplace transform of f1 of t minus tau plus Laplace transform of f1 of t minus 2 tau, and so on. Now suppose Laplace transform of f1 of t is equal to f1 of s, then what happens to this? Laplace transform of f1 of t minus tau. Based on a second shifting theorem, it becomes e to the power minus tau s into f1 of s. This becomes e to the power minus 2 tau s f1 of s, and so on. So in this, if I take f1 of s outside, it is 1 plus f1 of e to the power minus tau s plus e to the power minus 2 tau s, and so on. Now this is the infinite series and it is geometric in nature. So this is the infinite geometric series. So in case of the infinite geometric series, it is sum is equal to 1 by 1 minus r. So it is 1 by 1 minus e to the power minus tau s. So f of s equal to f1 of s into 1 by 1 minus e to the power minus tau s, where tau is a period and f1 of t is fundamental signal. So Laplace transform of periodic function. We have concentrated on Laplace transform of derivatives, integrals, properties, and Laplace transform of periodic signal. So we will study theorems related to Laplace transform in the next session. Thank you.